welcome everybody. We're here today for the Ph.D. viva of Guillem, Vallicrosa, and I would like to welcome everyone, the public and the viewers. You'll have 45 minutes to an hour to present your work, and this will be followed by a series of questions.
Thanks. Welcome you all, and thanks for coming. My name is Guillem Vallicrosa, and I'm here to defend my thesis on online acoustic localization methods for autonomous underwater vehicles that was supervised by Dr. Pere Ridao. As you all probably know, 71% of the Earth's surface is water, but we can only consider 5% of that surface completely explored. We have complete maps of the Moon or Mars, but we have not completely explored our oceans. This underwater exploration started with manned submersibles, where we have the pilot inside, which if we have any problem in the submersible, it can be bad for the pilots. We need big ships for deployment and recovery of those vehicles. But the good thing about them is that they are manned, so the pilot can react to what they see. Later appeared the remotely operated vehicles that put the pilot outside. The pilot is still operating the vehicle with a direct connection to the vehicle, but we still need big ships for deployment and recovery. More recently appeared the autonomous underwater vehicles, that they are completely autonomous, there is no pilot. We can deploy them, some of them from small ships, but the new challenges that arise from this is that because they are autonomous, we need a lot of work on algorithms to make them really autonomous. One of the biggest problems that we have underwater is that we don't have GPS, so we don't know exactly where we are. We don't have GPS because the electromagnetic signal doesn't go through the water. We have several acoustic aiding localization methods that are based on acoustic transponders, such as the long baseline, the short baseline, the ultra-short baseline, and the GPS intelligent voice. But all these methods require deployment and or calibration that makes the process quite slow and expensive. If we want to explore our oceans, we have two challenging scenarios where we can make a difference. The first one is if we can have a vehicle that is permanently deployed underwater, we can continue monitor a place, and we can contribute to the permanent observatories. Another one of the challenges is that if we want to continue exploring the underwater, we have some challenging environments like underwater caves and under ice, where we don't have these acoustic aids. Looking at these problems, we have the first one. We can find it in the oil and gas industry and in the offshore wind farms, where we need a vehicle to stay in a docking station that does continuous exploration and checks for any defects on the installations. The base serves several functions. It's for recharging the vehicle and also for receiving and transferring data back. The problem that we have here is that our vehicle, while it's doing the mission, will drift and won't know exactly where the docking station is. So the solution to this problem that we need something that provides a long-range localization to know where our base station is. We, of course, need it to be autonomous, and we want it to be as inexpensive as possible. For that, we're thinking about acoustic ranges because most of the autonomous underwater vehicles already have acoustic modems. And in the scope of this thesis, what we are proposing is a range-only localization method. Regarding the other challenge, autonomous exploration, we want to be able to explore cave and under ice and fully 3D environments where we don't have these acoustic aids to properly localize. And usually we have bad visibility with cameras, so we need a method that works with sonar. And we need to build a map that is meaningful for path planning. We don't just need a map with some features, we need a dense map of the world. And for this, the solution that we need is that we obtain an occupancy map. An occupancy map is a dense representation of the world that tells us for every point in the world if it's the probability of being occupied or free. And of course, we need it to run online. And for this, on the scope of the thesis, we are proposing the Hilbert-Slam framework. So now that you expose the motivations of the thesis, we can state the goal of the thesis, which is to research and develop advanced online acoustic localization methods for AUVs, and we are proposing two distinct methods. One that localizes an AUV on a docking station in the context of a remote launch and recovery application, and the second one that localizes an AUV using a continuous occupancy model. This goal can be broken down in several objectives. So we have the two algorithms that we propose for the challenges. The first one, the online localization method for the docking station. We want to do it only with range-only localization, to extend it to active localization, and finally to extend it to full SLAM. For the online occupancy-based SLAM, what we want to do is to have an efficient representation of the wall that we can run online. Finally, we don't want just to demonstrate these methods in simulation, we want to demonstrate them on real data and, if possible, in the vehicles themselves. So now that we finished the introduction, we see that we have the two main blocks that are related to the two challenges that I presented, and then I will finish with some conclusions. Starting with the first block, let me remind you about the problem that I was talking about. So we have a vehicle that has a docking station, and the vehicle drifts during the mission, and we need to go back to the docking station. For this, we need a long-range localization. It has to be autonomous, and we are going to use only acoustic ranges. The problem of acoustic range localization is that with a single range, it's very difficult to know exactly where is the docking station. In 2D, this problem can be solved if we have only 3 measurements, we can know where is the docking station. And in 4D, if we have 4 measurements, we can know where is the docking station. But these are the ideal cases, of course. In the real world, our measurements have some uncertainty, but at least we know that the docking station is underwater. So we are in front of a highly nonlinear problem that cannot be solved with an extended Kalman filter, because extended Kalman filters use a Gaussian for representation of the uncertainty, and if you use a Gaussian to represent this uncertainty, the mean of the uncertainty will tell us that it's on top of us, and we know that the docking station is not on top of us. So looking at the state of the art of range-only localization, we found that we have some offline methods and some online methods. Starting with offline methods, first we have a method that relies on the least squares approach. So we get all the measurements and all the navigation from the robot, and at the end of the experiment, we can locate exactly where was the docking station. Another one is to use a voting space similar to the Hood transform, that from all the measurements, we can also locate the docking station. There is also one that does a maximum likelihood estimate, also at the end of the mission, but in this case, it's a moving acoustic transponder. And finally, for the offline methods, we have a moving horizon estimation that uses a window of the last measurements to estimate the current position of the docking station. Moving to the online methods, we have the ones related to the particle filter, so we spread particles on the wall, and the ones that survive tells us exactly where is the docking station. And finally, we have the sum of Gaussian methods, and then instead of using particles, they use Gaussians, and also after all the measurements, some Gaussians survive, and those are the ones that provide us with the localization. Because we want a method that is capable of running online on the vehicle, and because sum of Gaussian is less computationally expensive than the particle filter, for this problem, what we choose is to start from a sum of Gaussian filter. So going to the sum of Gaussian filter, we can explain what it is. It's similar to a particle filter, but instead of particles, we are using Gaussians. And the good thing about that is that we can apply extended Kalman filter updates to those Gaussians. So basically, we represent our uncertainty on the localization by a weighted sum of Gaussians. Here we can see an example of covering the same uncertainty space. We need a lot more particles than if we are using Gaussians. We are also covering more uniformly the same space. This sum of Gaussian filter, we initialize it with the first measurement. So when we get the first measurement, we spread all the Gaussians in the possible locations. And one way to do it is to take a tangential covariance. So we set the size, the width of the Gaussian, and we spread all the Gaussians around all the possible positions. So once we spread them, we have our initialization. Another way to do it, if you wanted to bound the computing power of this algorithm, is to use a geodesic grid initialization that is based on the subdivisions of an icosahedron. So once we know how many Gaussians we can process in one sensor update, we can set the maximum number of Gaussians that we will use, and we will know that we can compute everything online. And here we have the initialization. But for now, we are going to use this one. Here you can see a simulated example of the localization, and you can see the symmetries that appear when we move straight. But when we change the directions and we have a more observable trajectory, we can see that we correctly locate where is the docking station. So going to the main filter, as we said, is very similar to a particle filter. So we have an initialization where we put our Gaussians, and then we have prediction weighting and resampling as all the particle filters. So going to the sum of Gaussian filter, what we keep in the state vector of each of the Gaussians is the x, y, and z position of the docking station, and we use the AUV navigation to know where we are. For the initialization, as I said before, we use the first range measurement to spread all the Gaussians. And then for the prediction, because we have a static docking station that is on the seafloor and doesn't move, we are not doing any prediction. And then for the weighting, we are combining the extended Kalman filter update and taking the innovation of this update to update the weight of each of the Gaussians. Finally, we are not using resample because if we don't have a prediction, the particles are not moving, and if we resample, they will be in the same place, and it won't be worth it because they represent the same thing. And we keep doing this until a required threshold is reached. The problem with this threshold is that if we have several Gaussians, how do we know that we reach that uncertainty that we want? For example, if we had 3 Gaussians in our sum of Gaussian, one thing that we can do is we sample 1,000 random points from each Gaussian, and we compute the equivalent Gaussian of those 3 Gaussians. Another way to is the computational power that we need is to use the uncentered transform and only sample the point that the uncentered transform tells us, that in 2D it's 4 points per Gaussian, and then we compute the equivalent Gaussian of those points. If we compare the 2 equivalent Gaussian, the one that we obtain with 1,000 points and the one that we obtain with the uncertain transform, we can see that they are quite similar. So we can use this, this approach to lower the computational power. Also, if we need an autonomous localization of the docking station, we have 2 ways to do it. Either we fix a trajectory that ensures observability, or we let the vehicle decide at each moment where to move next, which is called active localization. For this case, the active localization that we propose is a set of 26 actions that are 3 meters displacements in several directions. And what we do is we evaluate the uncertainty that we will have a posteriori, because in the extended Kalman filter, you can evaluate the uncertainty that you will have on the future without having the actual measurement. And with this, we compute the entropy, and we go to the action that has less entropy, because reducing the entropy is the same as reducing the uncertainty. Now that we know how our algorithm works, we are going to test it in some real-world experiments. And for this, we are using Girona 500 AUV, where we have an acoustic modem that provides us the ranges. And we have a forward-looking camera to check the acoustic localization against visual localization, to have a kind of error measurement. So for this experiment, we use a floating panel that acts as the docking station that we want to find. We have the acoustic modem on the docking station. And once we finish the localization below the threshold, what we do is we do an approach trajectory and turn around the docking station so we can check visually if we found it correctly or not. For this, we do a total of 12 experiments. 4 of them are teleoperated, and 8 of them use the active localization that I just explained. And they all start in different positions, random positions. You can see here an example experiment. So the vehicle is deciding where next to move until the localization is below a threshold. And when it's below the threshold, the vehicle checks visually that we correctly found the docking station. Here we can see the trajectories of all these 12 experiments, the 4 that were teleoperated and the 8 that were doing active localization. The dashed line that you can see is the approach trajectory to check visually if we found it or not. In black, you can see the visual localization, and in color, it corresponds to the localization of each trajectory. This black circle that you can see here marks a 4-meter distance from the docking station. That is what we consider that we need to do a proper visual localization. Here you can see 2 examples of experiments with all the range updates and the final visual and acoustic localizations. Also, as I said, when we use active localization, what we aim to do is to reduce the entropy. So we check for all the active localization experiments that we are really decreasing the entropy of each experiment. So we see that at each step is where we got a range measurement, and we see that for all the experiments, we are always reducing this entropy. We can also observe that in experiment 10, we had a lot of time without any range update, but still we got a proper localization at the end. All these experiments that I explained, we saved them using the robot operating system back files, and then we wanted to try different variations of this algorithm. The first variation that we wanted to try is knowing the depth of the docking station. So if we know the depth in our state vector, we only keep x and y position of the docking station. And then what we need is to project the range to the 2D plane. So when we have a range measurement, because we have a pressure sensor, we know where our vehicle is in Z, and the docking station has either a pressure sensor or we know exactly at which depth we put it. So we can project this range measurement to use it in our filter. The other variation of the algorithm that we want to try is a full slam. So in our state vector, now we have the robot position, the robot velocities, and the docking station position. This is similar as having a particle filter where each particle is a complete navigation filter. And the good thing about this variation is that it corrects the vehicle drift that we were not doing in the other ones. If we compare the 3 algorithms, so the 2D, the 3D, and the SLAM, we see that they have similar performance, and that they all have an error below 4 meters that is required for the visual localization. And because they have similar performance, we are going, and they are from the 2D to the SLAM, they are more and more computationally expensive. We are going to use the less demanding one if we can. So if we know the docking station depth, we're going to use the 2D localization. If the drift is small, we can use the 3D localization. And if we have a big drift, we can use the SLAM one. So now that we've seen that our range-only localization algorithm works alone, we're going to test it in a bigger project with other methods. This bigger project is the Lundok project, which is part of the European project Sunrise, where we develop a docking station for Sparus 2, and we develop also the algorithm for autonomous homing and docking. The final experiments were done in Italy, and the objective of this project is we have a robot in the docking station, it receives a mission, it undocks itself, it goes, it does the mission, and then when he wants to come back to the docking station, it does a homing and docking procedure. And finally, when it's already docked, you can download the data that get collected in the mission. So if we look at the homing and docking, because it's where we can do range-only localization, we can see that we have several approaches combined. So when we are far, we have a long-range acoustic localization, which is the sum of Gaussian filter that I already explained. Then when we are closer, we have a short-range visual localization. So we have some light beacons on the docking station that was developed by one of my colleagues in the lab. And finally, we also have a line of sight controller that takes care of always having the light beacons inside for the final docking maneuver. You can see here that we have the acoustic modem that provides the ranges, and in front we have the light beacons. For this project and the range-only localization, we had some new considerations that we have to take into account. We can have obstacle nearby, so we have the harbor and we have a lot of buoys and there is a lot of traffic. So we decided that instead of using the active localization method that I explained before, we use a fixed trajectory that ensures observability. So we execute this trajectory that turns a lot and changes a lot of directions. And when we achieve the required threshold, we abort the trajectory and we keep doing the homing and docking. We also wanted to have more precision because we realized that when we do a localization here, we have a lot of tangential uncertainty. So we decided to add an extra point where if we move there, we reduce this tangential uncertainty. And finally, also the docking station sends us the depth and orientation every time that we ask for a range. So we can do the 2D localization. The general strategy for autonomous undocking is this one. So we have the vehicle that wants to come back to the docking station, doesn't know where it is. So we first start with the fixed trajectory to have a first estimate of the docking station. When we find this estimate, we move to the extra point to reduce the tangential uncertainty. And then we go to this estimate and we keep looking right and left until we see the light beacons. When we find the light beacons, what we do is we do the final docking maneuver. And this is a very complex project, so we did some incremental testing. We started testing everything on simulation, then we tested the final maneuvers in our water tank in the lab. And then we tried everything in the coast nearby in San Feliu, and finally we went to the final location in Italy. In Italy, we put the docking station at 9 meters depth, and we did a total of 15 missions with undocking, mission, and docking back. Regarding the range-only localization, it always worked. We always found the correct position of the docking station. But sadly, regarding the docking, we had 3 experiments that failed because in 2 times we had a strong lateral current and sparrows couldn't go inside the docking station. And 1 time the camera failed. We couldn't see the light beacons, but still we dock with only the acoustic localization. But because the algorithm uses the light for the final maneuver, we consider this as a failed experiment. You can see here the full trajectory for one of the experiments. So in violet, the vehicle undocks. In orange, it does the mission that we requested. In black is the range-only localization. And finally, in brown is the looking for the light beacons and finishing the docking. If we just look at the range-only localization, you can see here that we start the trajectory and in a moment we already are below the threshold, and then we move to the extra point and we reduce a lot this tangential uncertainty. You can see it here, that is reduced a lot. And finally here you can see a video of one of those experiments. So Sparrows is undocking. You can see that the visibility is very bad, so you really need an acoustic localization method. You can not only rely on the camera. Here is doing the mission. Now that it finished the mission, it starts the range-only localization with the start trajectory. We can see here the uncertainty that is getting reduced tangentially. Now it's going to the estimate position to find the light beacons. Now you will see the camera on the right. So it's looking left and right for the beacons until it sees the 4 beacons, and then starts the final docking maneuver. Until we correctly dock in the docking station. So to recap this section, what we presented is an acoustic range-only localization based on the sum of Gaussian filter. We did several variations of the algorithm. We also developed an acoustic localization method. All these run online in the vehicle. We got a precise localization that is enough for visual docking. And finally, we integrated our algorithm in a bigger project combined with other algorithms to have a full homing and docking approach. Now that we finished with the first challenge, we go to the second challenge. Let me remind you about the problem that we are trying to solve. So we don't have acoustic gauge for localization, and we want to explore complicated environments. And we need a map that is meaningful for planning. So we want to provide the map for this autonomous exploration that has to be combined with some autonomous path planning to achieve the whole exploration. So we want to obtain an occupancy map that is meaningful for this planning. We want it to run online, and for this, what we propose in the scope of the thesis is the Hilbert SLAM. And because we want to do SLAM, we taken a look to the state of the art in underwater SLAM, and we found that there are 2 main categories: the optical SLAM, so with cameras, and the sonar SLAM, that is classified by the type of the sensor that we use. Regarding the optical SLAM, we have the 2D photomosaics, that is probably the most widely used of cameras underwater. So we collect a lot of images of a more or less flat zone, and we do a combination of them to have a photomosaic. If there is more 3D in the seafloor, what we have to do is a full 3D reconstruction of the environment. Regarding the sonar SLAM and the forward-looking sonar, that we obtain an image-like acoustic image. This is a mosaic obtained by features in the acoustic images, and that is a Fourier registration of forward-looking sonar. Regarding the multi-beam echosonder, we have a method using submaps to find the SLAM solution. We have a method relying on the particle filter, and then we have a method relying on the probabilistic ICP. Finally, on the mechanical scanning sonar part, we have a method relying on line features, a method that provides an occupancy octree, and a method relying also on the probabilistic ICP. From all these methods that I presented here, only these 3 are demonstrated to run online. And from these 3, only this one provides an occupancy representation of the wall. So looking at the Fairfield paper from 2007, we see that he uses a sonar beam measurements. He also uses a raw Blackwell-ized particle filter, so it combines the extended Kalman filter with a particle filter. This particle filter, each particle carries a map within which is an octree occupancy map. And he uses a mapping inheritance to avoid too many copies in memory. Because we want to do a SLAM underwater and we want an occupancy representation, we keep this method as a reference, but we want to do another representation of the map. But before explaining what is a Hilbert map, let's start what is the occupancy representation that I'm talking about. So occupancy representation, as I said, it describes the wall with an occupancy probability for each point that we have in the wall. This is very useful for path planning. That is what we want to use it for. So it's a dense description of the wall. And the probabilities of occupancy help us decide which is the safest path to take. There are several representations of occupancy maps. The oldest one is the occupancy grids. Then appear the quadtrees and octrees to save memory. And recently we had the development of Gaussian processes occupancy maps that represent our map by the relationship of our observations. And even more recently appeared the Hilbert maps that, that I will talk a lot about them later. All these occupancy representations have different characteristics, like the first two assume that there is a independence between the cells. So if a cell is free and the two nearby is free also, we don't know anything about the one that is in between. But the two other methods, because they are based on the relation between the observations, there is no cell independence because there are no cells. Also, the Gaussian processes provided us, apart from the probability of being occupied, it also provides us with the uncertainty of that probability. The resolution that we get from these methods, from the first two, is set at the beginning. So we set the cell size, and that's the map that we will get. And for the Gaussian processes and the Hilbert maps, we have infinite resolution, so we can query them at any resolution. In this case, in the examples that you see, they were queried at the same resolution that we defined these two for easy comparison. Looking at the memory that they need to save them, here we need all the cells of the extension of the map, even the ones that we never observed. In quad trees, we only save the cells that we observed at some point, so that we have some meaningful information. In Gaussian processes, we save all the observations that we have in the wall and the relationship, so that's why all the observations are squared, because we save a matrix of those observations. And in Hilbert maps, we save a value for each feature that we have, that I will talk about it later. Finally, another important aspect of this representation is the query complexity. So how expensive computationally is to know to query one point on this representation. So it's constant for an occupancy grid map. It's logarithmic because of the tree structure of the quad tree. It's cubic in the Gaussian processes because you need to invert a matrix in order to do the query. And in Hilbert maps, is constant. Now that we review the occupancy representation, we can see what really are Hilbert maps. So Hilbert maps are a fast approximation to Gaussian processes. They project the observations that we have in the real world to a higher dimensional space that is called the Hilbert space. And the good thing is that they can be trained or learned by stochastic gradient descent, which is a method that is able to run online, and it's incremental, so you can keep adding data to your model. And finally, this method of Hilbert maps was developed only for a scene representation and has never been used for localization, so we want to be the first one to do that. So a Hilbert space basically is a space that has an inner product. So if we multiply two vectors, we get a scalar. And what defines our type of Hilbert map is the feature map that we are doing. So how we transform our points in the real world to the points in the Hilbert space. For example, in this case, if we want to linearly separate by color these 4 points, there is no way that we can do it in 2D. So what we do is a feature map that projects us to a higher dimension where they are clearly linearly separable by a plane. And there are many types of feature maps in the literature, but we are only interested in the ones that are called the spar feature maps. So in the spar feature maps, what we have is virtual or inducing points in the real world in a grid for fast access. So for example, we have these virtual points in the real world, but we could have them like this in 2D or like this in 3D, but we are only focusing in the thesis in the 2D case. And if we zoom to these features, what we have is that they have a limited neighborhood, so they only affect up to a radius. And this is the feature map that we are using for transforming our points to the Hilbert space. So for example, if we have one point here, we can see that it's only affected by these 3 virtual points and not by the second one. So when we transform this point, we get this vector in the Hilbert space. Just let me introduce a few notation of how we are going to put the equation. So X is a training point in 2D. with a label that is free or occupied, depending on what we observe. M is the model that we learn, so our map, and X star and Y star are the query points. So when we know our map and we know the transformation of our query point to the Hilbert space, we can know the probability of occupancy using this equation. So as I said before, we transform this point to the Hilbert space, and we use the weights that we learn from each of the virtual points to know the occupancy probability. To learn this map, what we use is the stochastic gradient descent, as I said before, and we basically minimize the negative log likelihood. To explain it easy, the weights that we have now are the weights that we had before, updated by a learning rate that we set, and the difference between what we've seen until now and what we are observing now. So when we want to learn some new measurements, here we have the measurements, we have to sample them because we only learn points, and then we use the stochastic gradient descent to learn our Hilbert map point by point. Here you can see another example of learning, incremental learning of the map while the robot is moving. And as we see now, we have 3 different parameters that affect our Hilbert maps. So one is the resolution of the Hilbert map, which is the separation between these virtual points that we are putting. One is the radius of the neighborhood of the virtual points, and finally we have the learning rate. Here you have the default values that we are using, and if we compare different resolutions, we see that while we increase the resolution, we lose the detail on the map, and if it we lose the detail on the map, and if it's really small, the points that we sample are too far away and they don't affect enough neighbors. If we look at the neighborhood radius, we see that if we put it very small below the or equal to the resolution, the cells become independent, so it's like having an occupancy grid. And if we increase the radius, the points affect more points in the neighborhood, and also we lose a lot of detail on the map. A common value that is set in the literature to use is at least that the radius is twice the resolution. Finally, regarding the learning rate, it says how fast we learn from the observations that we have. So we see that the more high that we have the learning rate, the faster that we learn. But learning faster doesn't mean that we learn better. So now that we know what are Hilbert maps, I can show you what is the Hilbert SLAM algorithm that we are proposing for occupancy representation. And we are also using a raw back-realized particle filter because we can separate into the linear part and the non-linear part. So in the linear part, we have an extended common filter with the depth and the linear velocities of our vehicle. In the linear part, we have a particle filter with the XY position of the robot and the orientation. We put the orientation here because we had several problems with magnetic disturbances in our robots. And because it's a particle filter, we also have a weight for the particle. And finally, we also have the map that each particle is learning. Of course, this map is a Hilbert map. And finally, in the input vector, we have the roll and pitch and the yaw rate. So for the extended common filter, we use as a state propagation the constant velocity model. And for the state update, we use the data from the depth, DBL, and IMU sensors. In the particle filter part, also the prediction, we use the constant velocity model. For the weighting of the particles, what we do is we compare the range that we measure with the sonar with the range that we check in our learn map, and between this difference, we update the weight of the particles. When we use this new measurement for weighting the particle, we can learn it into our map in each particle, and finally, we resample the particles when the effective number of particles is below half of the number of particles. to be able to compare the sonar measurement with the expected measurement in a continuous map, what we do is we sample along the ray of our measurement until we find a point that is occupied. So when we find a point that is occupied, what we do is we take this point and the previous point that we check and we interpolate to find the final predicted range for the map that we learn. If we don't find any occupied point and we pass the maximum range of the sensor, we say that this ray measurement is free. Now that we've seen how our Hilbert-Slam algorithm works, we're going to test it first in simulation to ensure that everything works properly. So we have this data set for simulation. This is the ground truth, and this is the ground truth corrupted with some noise, both in the odometry and in the measurements. And before testing directly the SLAM, what we do is we test the terrain-based navigation or map-based localization. So we start with a known map. So we sample our environment and we learn a common map for all the particles, and we just do localization. Now we are not learning the map. If we run this algorithm through the simulated data set, we can see that in blue, the solution of the of the Hilbert terrain-based navigation, which is the solution is the particle that has more weight at the end of the data set. It correctly locates the vehicle, almost very similar to the ground truth, and there you can see the trajectories of all the particles that we use in this filter. You can see that once particles deviate from the main trajectory, they die and they get resampled into another position. If we look at the error of this experiment, we can see that it's clearly much lower than the dead reckoning approach. Now we tested in the full SLAM, so now every particle is learning their own version of the map. And we can see that even that we have a good correction compared to the dead reckoning, is not as good as we had in the terrain-based navigation. There we can see that there are 2 or 3 different trajectories that coexist until the end. And if we look at the error of all the positions, we can see that it's better than the dead reckoning, and it's also bounded around below the 2 meters. Maybe the results are not so clear why our method is better, but if we check the maps that we learn, we can compare the ground truth map, Hilbert map that we can learn with our solution, and it's clearly more similar than the dead reckoning one. Now that we've seen how our algorithm works in simulation, we can see how it works in some real data sets. These data sets were collected during view planning experiments by one of my colleagues in the lab, and we use Sparus 2 AUV with a forward-looking mechanical scanning sonar profiler. And the AUV is diving at 2 meters, so we don't have GPS for ground truth. The data sets were collected on the coast near San Felipe de Guíxols, where we have one data set that is a man-made breakwater and a natural rock a bit farther north. So in the breakwater data set, you can see that in blue you can see the trajectory that the AUV followed, and we have 3 events where we see something that we've seen before, so they are possible loop closures for our filter. And we can also observe the double walls that say that we had a lot of drift on the navigation of the robot. Looking at the rocks data set, we only have 1 loop around the rock, so we can only have 1 loop closing event, and we also see that we have a double wall. That means that we had a lot of drift. Applying the Hilbert-Slam method to the first data set, here you can see the dead reckoning, so what I already showed, and here is the solution with the Hilbert-Slam. As you can see, the blocks are much more square than before. We don't have double walls, only bit here. And the strange thing that you can see here is that we observe free inside the blocks. That's because we had some outliers that were not filtered out, and because we never observe again inside the block, we cannot correct that error. To compare this result with something similar to a ground truth, we can check with the aerial view of the zone, and we see that more or less they agree with the aerial view. And finally, if we check the covariance of the particles, we can see that clearly the three loop closing events that I was talking before. And here you can see in yellow is the particle that has more weight at the end, and is the map that is showing us, so the one that is collected by the yellow particle. And in green we see all the other possibilities while doing this algorithm. So you see that when they deviate a lot, they die and get resampled to another place. Now we had the first main loop closing. Now you see that these deviate too much and they die also. And finally, at the end, we have the third loop closing. Regarding the second dataset, the rock dataset, we have also here the dead reckoning and here the Hilbert-Slam solution. You can see here clearly the double wall that we had at the beginning, and here there are no double walls anymore. Here we don't have the problem with outliers inside the occupied places. And the only strange thing that we can observe here are these three occupied points on the boundary of our map. But if we look it in the aerial view of the zone, we can see that they correspond to the neighbor rock of the coast. And if we look at the covariance of the particles, we see also that we only have one loop closing event, as I said before. And here you have the full experiment. So now also it's showing the yellow particle is the one that is showing us the map, and the green particles are all the other options. As you will see here, the particles are spread much more than in the other dataset, because we only have one loop closure at the end, so there are plenty of possibilities. And we are also looking only forward, so it's difficult to see something that we already seen. And now when we see the beginning, several particles will die. They died here. And now a lot of possibilities coexist. If we had a longer data set, we'll discard them for sure. But this is the data set that we got. Finally, because we are interested if this really runs online, we compare the mission time, so what it took the vehicle to collect this data set, and we compare it with the time to run the Hilbert-Slam. And clearly we have enough time to run it online. And we even have extra computing power for the autonomous path planning algorithm that we need to combine with this to achieve the truly autonomous exploration. So to recap this section, we propose a continuous occupancy map with Hilbert-Slam. We did an online computation. We achieved a correct localization according to the aerial images, and we tested the algorithm both in simulation and in real datasets. Now that we've seen how we solve both problems, we are going to the conclusions. And we can see that we advance in the state of the art of underwater localization by proposing two online methods for localization. The first one is the range-only localization, that we use an online range-only localization for homing. We propose a sum of Gaussian initialization with geodesic grids to bound the computing power. We also propose a way to compute the equivalent Gaussian using the uncentered transform. We also develop a range-only active localization, and we integrated our method with other methods, and we did a lot of experimental evaluation in the real robot. Regarding the occupancy slam, we use the Hilbert maps for localization because they were developed only for representation and never used for localization, and we developed on top of this the Hilbert-Slam framework, and we did experimental evaluation also in simulation and on real data sets from our robots. So for the future work, what is left to do? For the range-only localization, we think that the next step is to move to a dynamic range-only localization. So we have maybe a moving docking station attached to a ship and we want to dock there. And for the occupancy slam, what we have to do is, of course, fit the outliers in our measurements to avoid the problems that we had in the breakwater dataset. We want to test how it runs in the real AUV, not just on data from the AUV. We want to test other sonar sensors like the multi-beam. We want to extend it to 3D. So using the multi-beam and probably up until we can do complete maps of the 3D environment. And we also want, of course, to combine it with online path planning to have this completely autonomous exploration. So finally, the Ph.D. roadmap that I had, everything started with the master thesis, which I did in terrain-based localization with Octomap. Then I had a research stay in Sydney in the Australian Centre for Field Robotics, where I learned about the Hilbert maps. These are where all the experiments took place, and these are the 3 journals that compose this thesis compendium. Apart from that, there are other publications on conference related to the work in this thesis, and also some collaborations with other researchers in many other conferences. Also, meanwhile in the thesis, I work in a lot of projects, both national and European. And to finish, just thank all the people in the lab for all the help in doing this thesis. And if you have any questions, you can ask.
Thank you very much. So we're going to open the floor to question, and the first to ask a question will be Stephen Williams.
Okay.
Well done, Guillem. I think you wrote a good thesis and presented very clearly. Good presentations. I had a couple of questions that maybe we can sort of tease out a little bit more detail. I guess I had a bit of a question about the observability analysis you did for the acoustic localization.
Okay.
So it's based, I guess, on a Kalman filter, and you're kind of assuming that everything's linear.
Mm-hmm.
If it's a range-only observation, presumably the filter update does depend on the observation. So how do you do that optimization? Like when you had a vehicle and you were selecting from 20-something different possible movements?
How we decide the trajectory?
Yeah. Can you just
elaborate
a little bit more on
the fixed trajectory?
Yeah.
So the fixed trajectory only ensures that you turn in a lot of different directions, which is what is required.
You had a picture with the vehicle with a number of different possible maneuvers that you were going to do, and then you said you picked the one based on the expected decrease in certainty in the entropy. Can you talk a little bit about sort of that process?
So how we decide this? We just wanted to cover a lot of possibilities, so we put on the plane at 45 degrees one movement each, and then at 45 degrees going up and going down is the 26 actions. So we cover a bit moving in any direction.
And then so you assume that you've got to a particular position.
Then you assume that you got there, and you just compute the updated covariance of all the Gaussians.
Okay.
And then you compute the entropy of all those Gaussians together, and then you get a value of entropy for that movement.
Yeah.
Then you do it for all the movements, and then the lowest one is the one you decide to move there, because it's the one that...
And how sensitive is this likely to be to the resolute, sort of number of initial Gaussians that you put in and sort of the uncertainty that you model at the start?
Yeah, if the Gaussians were bigger, probably you should propose bigger movements, because if not, they don't change so much when you move on the...
And then, sort of in the next experiment, you then went to a fixed pattern to try and find that. Is that sort of an intuitive fixed pattern, or could you derive an optimal trajectory that would make the problem?
For what I think in the literature, to derive the optimal, you have to know exactly where the docking station is, and then you can do the optimal observability, which is like a spiral going to the docking station.
Yeah.
But if not, the only limitation that you have is that you should never move always straight and never move directly to the docking station, because then your lateral uncertainty is increasing a lot.
Yep.
So you need to change directions to ensure that you find it. This is probably not the most optimal one, but it's something that ensures it.
Okay. And once you've found your estimate of where the docking station is, you then had a sort of a second maneuver to triangulate the position.
So we set a threshold that says that the biggest axis of our final uncertainty is below, in this experiment, 1.5 meters.
Okay.
But because we want to have even a better estimate, and we want to know exactly if it's here or here, we thought it was better to move regarding this axis of uncertainty to an extra point and reduce that.
So is there an ambiguity though there in the direction the docking station is actually pointing?
No,
so
because
can you come up the back of it somehow?
for the range-only localization, you just know the position. You don't know the orientation. It's impossible.
Yeah.
But in the case of the Lundok, because the docking station sends the orientation, that is what we use to start the search of the lights, because we know where it's looking.
So
we know where.
Direction of the docking. Okay.
So if we know that the docking station here and it's looking in this direction, we'll come from here to find the lights.
A couple of questions also about the Hilbert maps. So when you're doing the update, you said you were doing an interpolation from the occupied to non-occupied space. Can you use the free space to help in your update of the vehicles or the weights? Or do you only use that transition from occupied to unoccupied?
So what we do is we compare ranges. So only if we have a range measurement, we can compare it. Here, to get maybe a more precise way, you could divide the middle point and then keep dividing until you get more resolution for range. And to use the free space, I've been looking a lot at the literature on how to use when you have a range but on your map is free, or the other way, and it's not clear how to do it.
Presumably, if your map said there was something between you and the range you just got, that tells you something about the feasibility of that.
Actually, we use the model from probabilistic robotic that has a probability for having a short measurement and a random measurement and a maximum range measurement.
Okay. Guess one thing I think of I think would have been interesting to compare the results here to other map representations.
Yes.
So, can you at least speculate on how this, the Hilbert map representation would compare with? You had an example of different map representations. So, if you were to do the same kind of SLAM approach with those four techniques,
the easy one to compare here is that. It depends on the resolution that you choose for your occupancy, because that will give you a better estimate of your wall.
Yeah.
Here we only have to choose the resolution of the feature. So the difference between these resolutions, which in Hilbert maps is always more spread, and you don't need so many, it's the big difference in memory that it makes.
Yeah. Well, you can see there's kind of the walls are a little bit smudgy. So that has implications for path planning. It would be kind of interesting to have explored, with the data sets you've got, how these different methods compare. But maybe tease out what the main advantage that you think for the Hilbert is.
The lower memory that you need. Yeah. So it's I don't need to use an approach like Fairfield that uses the inheritance of the map to don't copy, because my maps are so cheap in memory speaking that I just copy them when I copy a particle.
All right. So the sort of bookkeeping associated with the map.
Yeah, at the end is like 1,000 values.
Yeah.
That's your whole map of the world.
Okay. And I guess you talked a little bit about sort of extending to 3D. Can you talk a little bit about what the main challenges with that are? And you mentioned using sonar, but we were just in the lab and saw the new laser. Is it something that you'd be interested in potentially trying out with some of the laser data?
Yeah, potentially. The problem with 3D is that we don't have any data set that we say, okay, this data set is good for doing a complete occupancy representation.
Yeah.
I've been trying with a data set from Aguilos, or from the cave, but the problem is that the lateral sonar that you have is a micron, so it opens like 20 or 30 degrees, and you don't know exactly which point are you looking, and that's like introducing a lot of outliers in the Hilbert map.
I used to try with the laser and that structure that you got on the bottom of the pool, because there you got some good structure and some interesting features.
That's pretty new, so we haven't had time to.
So but there's no significant challenge in going from 3D.
It's only you have it your grid in 2D or in 3D, and it's the same. Checking your neighbors and checking the values of the neighbors.
And I guess finally, you mentioned the challenges of outliers. You got outliers that end up in the middle of the map, and sort of there is a bit of a data association problem there. Is it something that you think could be addressed, or is that?
I can think about two things. One is to tune exactly what learning rate we need. So when the first point that we see is an outlier, then we can learn on top of it and have the correct map. But maybe we still have holes in things that we should never see.
Yep.
And the other is to have some kind of keeping track of all the measurements that we have, and we just update the map with some delay once we check that in some way that the measurements are similar and they are not outliers. But we haven't tried yet.
Good. That concludes my question. Thanks.
Yeah, thank you.
Okay, so Rafa, it's your turn to ask questions.
Great. So thank you very much, Guillem, for your presentation and just for introducing the concept in a smooth way, because I know you have carried out hard work, and I think part of one of the important aspects that I would like to stress is that what you're doing is something that fits very well in the team effort of the lab of just developing technologies that allow us to attack different problems from different perspectives, and it sits on the research of the lab. So thank you very much for the presentation and for the document. I'm going to ask you a few things that basically are curiosities and things in which I want to assess what is your grasp of the concepts of what you've been using. The first question is related to the localization for the documentation. When you were describing this way to initialize the sum of Gaussians, and at the beginning you needed to, I was wondering here, if you go back to this part of this representation here, if I compare this to this icosahedron representation, which you have covering a full sphere, here you are limiting yourself to a given range. Is this because you assume that you have a knowledge of the depth?
This is actually in the harbor in San Feliu. So
you're limited by
you say
water.
At least is 1 meter depth, and there we only have 12 meters. So.
All right. If you were doing this in a place, imagine that I want to do this with a ship that it's sending one of these aggregation devices for QNAS, for instance, and it's docked there, and you don't really know the depth. This means that the same approach you would be covering the complete sphere, right? Yeah. And this leads to the second question.
But if you know that it's on the seafloor, it's different. It's much easier.
Or if you know the depth,
it's not on top of you.
That's right. But then I was surprised. If you go to slide 28, when you were talking about active localization, and you described the 28, it's the previous one, but where do you see all the intersections? Like here, if I look to the right, basically here you are deciding how to move, or the robot is deciding how to move.
That one.
To improve or to have a better visibility. But I have the feeling that this trajectory probably is still keeping the tangential uncertainty quite large. Whereas maybe getting these circles to be more orthogonal in the intersection will give you a better estimate.
If you don't finish with the threshold and you keep it running, at the end
it
starts turning around, so you get just a point in the middle.
And what is the condition that makes it turn?
It's the one that I explained with the entropy.
This 1.5.
Yeah. To finish is, the biggest axis of the uncertainty, it's lower than 1.5.
All right. But I have this feeling, I don't know if this is just a sample of the examples that you chose, but I had the feeling that when you were doing this active localization, most of the time you ended up with this type of uncertainties.
If we look at the trajectories, all are quite similar. So they start moving, trying to move around.
And how does this compare to this star that you were using in the experiments?
Okay, the thing of choosing the star or another trajectory.
No, in terms of how this is affecting the tangential uncertainty.
It's similar because you move only in a small area. So what affects more the tangential is how far you are from the docking station on your zone of movement.
Yeah, but basically, I was thinking, just looking at the data as it is, that normally moving in longer or having longer transects, once you see where you have this tangential uncertainty, will decrease in a faster way.
But the problem is that this was also in a harbor.
So
we couldn't move here.
Okay.
We couldn't move here.
All right. And then I have another curiosity on slide 32. You were showing the results of the different algorithms, and in blue, so you have one experiment in which you have some experiments, like experiment 8, for instance, where SLAM is performing much better. But in some of the experiments, you have very similar performance. Well, I expected the SLAM to work better. What is your take? I would expect it to have less drift.
But the trajectory is so small that you don't have drift almost. So doing a SLAM or not doing a SLAM, it's almost the same.
Yeah, but look at experiment 2, for instance.
Yes.
It's quite surprising that
Yeah.
you will get. And then the surprising thing is that then you conclude that you would use a SLAM, like the last line that you have there in the slide, when you have a big drift, which is somehow I have the feeling that maybe this is not so representative of the type of experiments that you were running to conclude what you're concluding.
Okay.
So it's more like you're using common sense than your data is proving your conclusions. So you think that it's only because of the size of the
the trajectory was like less than 10 meters.
Okay.
Less than 30 seconds. So.
All right. And just a final question on the localization of the docking station. What was the visibility when you went to Italy and you show us this video?
As you've seen on the video, or as you've seen here.
Are we talking about 2 meters visibility, or?
I actually didn't go to the experiment, so my code went to the experiments, and they didn't call me to solve any problem.
which is good news.
Which
so
is
far.
good. And I think they had like 6 or 7 meters where you can just see the points of the lights, and because they are very powerful. You know, in the video. In the video, you cannot see anything else.
But at 4, you're already seeing.
So here, it's because the lights are very powerful, because you cannot see anything else underwater. And here you can see that until you are very, very close, you cannot see the docking station.
This is not real time anyway.
No.
The video, I mean, it's figured out, right?
A lot, yeah. The docking is much slower and smooth.
Okay, and going to the Hilbert plan, I would like to know. I was having a hard time. It's counterintuitive for me in the beginning. I didn't know anything about Hilbert space, and I just looked at it and I saw that they use it in quantum physics and some applications that are out of the things that we normally do, and using Hilbert maps. I think it's a very interesting contribution of your thesis for doing the SLAM using this framework. I was surprised to see that when you increase resolution, you lose detail in the map. So it's like something that is counterintuitive.
Yeah, maybe it's not the best name for the parameter. Because resolution is the distance between the points and not,
okay.
Yeah. So it's
All right.
It's the inverse of resolution.
So in fact, what I wrote here is how sensitive are the parameters to the performance. So this distance between features and the radius. But somehow you also said that the radius normally is twice.
Yeah,
the
1.5
so at the end, it's
twice.
like if you tune, you only need to
Yeah,
tune one
basically
parameter.
you tune the resolution, which depends on the details that your environment has, which is something that if you do completely autonomous exploration, you don't know beforehand, but you have to estimate something.
Okay.
Did you try with different ratios between those two things? So, 3 times or?
Yeah, no, actually. This is 1 time, 2 times, 1.5, no, 3 times, and the resolution. So too many.
And 2 times is like the
too many points interact for a single measurement, and then they all affect each other, and you lose the resolution of the.
Well, this is a very obvious outcome of what to choose. Assigned. And looking at the document, in page 63, you justify one of the nice things about this is that the amount of memory that you need is much smaller than what you would need without using this representation. But I did the numbers. You put an example here in which you say that if you represent a map with doubles, 8 bytes per double, blah, 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 you have 545 kilobytes for a map that then you represent with a Hilbert map, and it takes 21. And then you say, this is 4%. And what you write here is that this is 0.04%, which is
it's a typo.
It's a big gain, but it's not that big. So it's, probably this is thinking in taking one as the absolute. I mean, 4% is a great increase. Just at the beginning, I saw it and I thought, wow, so this is really
it's a typo.
5 orders of magnitude. Yeah. Okay. But the nice thing, and I think this is something that Stefan commented before about, basically your map representation gets very smooth.
Yeah.
And this might not be convenient for making a robot navigate here in this room, but in underwater things tend to be quite smooth. So if your objective is path planning at the end and knowing how to replan the trajectory of the robot as it's in the water, probably this is not a problem. What is your take on that?
Yeah, what we also put in the same paper is that although it's not good for closer environments, it seems good for underwater where everything is smooth. But anyway, there are other kinds of features that you can use that they develop after I started my work, and they have some features for representing walls, so they have perfectly square indoor environments also for representation for now.
And the only change will be that you use different types of
the future
features
mount that you use. But it's not a grid, it's not so fast to access. They use different features in different positions. Each one has a different neighborhood, so you need another structure to save that. So
then this means that the computational cost of the query will be different. Okay, which is one of the strong points of this representation.
Yeah, that's why we chose the easiest one, because it's the faster one.
Okay. All right. I think just have a. Then I had another comment on. You've been using Hilbert's LAM on a 2D approach. And, in fact, you've been addressed a question in this direction. My question was, how does it scale from a computational point of view to 3D? Is this still going to be achievable by using the hardware of the robot itself, or are we jumping And
It depends a lot on the resolution and the neighborhood that you choose. So if you keep your neighborhood in like, if it's 2 times the resolution, you have less than 11 points to check per point measurement that you want to add. So I think it's still feasible. Or you choose less resolution, you have a faster map but with less detail, that probably is enough for the path plan.
okay.
And then when you get your robot back from the autonomous exploration, you can do post-processing and do a proper 3D.
All right. Stepping on the computational cost, if you could go to slide 73, there was
Which one?
73. It's you were showing the performance. This computer that you have here, this i7, is not the computer that is running in the robot.
No.
Right?
But I
But
think
it's still an i7 in the robot.
yeah, I think this computer is worse than the one that we have in the robot.
Sorry?
It's worse than the one that we have
It's
in
worse.
the robot.
So even it's the advantage, I would say. Of
I haven't checked, but
All right. Okay.
but
So
this is like from 7 years ago, and the robot one is 3 years old. Although that is smaller, I think.
so performance is supposed to be
similar.
even better. That's fine. Okay, so from my side, just congratulate you again for the work, and well, I hope we'll see the future work coming to results in the near future. So, thank you very much.
Thank you, Rafa. So it's my turn. So I really enjoyed the presentation. It clarified some of the stuff I hadn't fully grasped, I think, within the manuscript. And it's nice to see work that is applied in the real world, because I know how hard it is to actually go there to experiment, get your data, and so on that point, it's really good. I enjoyed both aspects of the work, actually, the range order and the input lab. I've got a few questions. It's quite interesting that everybody is kind of moving on the same areas. So overall, in general, I think you've missed a trick in not comparing your work very much to what's there, because I think it would have probably a much bigger impact if you were able to say, like, in this graph compared to what was done before, that's the gain.
Yeah.
And the gain will be memory, computational speed, and that's the loss of performance, depending on resolution. I know it depends on the resolution of the frequency. But I think it would have been really nice to place your work in the context of what's been done.
Yeah. The problem.
But you tell us it's working.
The typical problem with that.
I've tried it. It's working. Well, in simulation, I'm not saying on real data.
Yeah, but
there are algorithms.
The problem that you have with that is that usually people don't put publicly their code, so it's up to your implementation of what you read from other people.
Yeah, but in the terms of the black polarized particle filter, using the standard technique, I think that code is there somewhere.
Okay.
But also, so I've also got the question about comparison. So say on the observability, discuss that with Stefan. So you've got 3 approaches. I think one is you define a specific trajectory. One is the active, and then the final one is this kind of star-shaped.
No, but this is
which is
a
also a specific
predefined
trajectory.
Yeah, I don't say that is a new one. We have the predefined that we use on the Lundok, and we have the active that we use on the first experiment.
Yeah, so it would have been nice to compare active versus static. What do I get?
Okay.
Is it worth bothering with doing the active? And when you do the active, you go 3 meters.
Yes.
That's your why 3, why not 1, why not 5, why not 10? You know, again, it would have been nice to say, okay, if I do active, if I do 3 meters, that's the trajectory I get. If I do 5 meters, if I do 20 meters, because it might be that your lateral, see, the fact your trajectory are all seems to be just not doing very much. I think it's because you constrain it to 3 meters. So it moves 3 meters and it looks around and you go, okay, I'm going to move a bit in. And you might not have enough, you might have noise in your in your covariance matrices, which doesn't drive it. So this graph is all for 3 meters.
Yes, but my answer is that was not the biggest problem, choosing where to move, because the biggest problem that we have is that range observations are not very reliable.
Yeah.
So we had more problems waiting for receiving range updates at any movement, because with Girona you have the modem on top and the logging station was a bit down. So a lot of times you couldn't measure because the robot was in the middle of the sensor. And yeah, we had some problems with that, and we didn't test other distances or.
So on the range localization, I've got another question which maybe is a bit more fundamental. You're saying your technique is the online. A lot of the other techniques are going to be for art.
Yes.
Because they use some kind of delayed state filter.
What?
So, I mean, one of the technique you could use is to say, right, I need 4 measurements to get the 3D point.
No.
I'm going to just measure four measurements. I'm going to move using my either active or just a standard.
Yeah, just 4 points that you refine.
I get my 4 points, that gives me an estimate.
Yes.
And I can do that in one go, boom, done. And I can then do it again. When I receive a new measurement, each time I get the 4 of the end and I do. And that surely can be done online.
Yes.
You only have
That's another approach to it, but if one is an outlier, here we are keeping all the measurements while we move.
You keep what you told, there was one of the slides you showed, they keep a window.
Yeah.
And you can then do outline rejection. I mean, there's lots of things you can do.
Yeah.
So, but you kind of classify that as offline, I get the impression, at the beginning.
No.
So why is it not online then? And again, it would have been nice to see a comparison, or to at least reflect on what you've done with respect to what was gained.
So here what we classify offline or online is because
so the moving around
in the paper they say that they only use the data once they recover the vehicle.
Yeah, that might be because they couldn't do it online for other reasons.
Yeah.
But it would have been nice to see a reflection at the end of saying, okay, these are the techniques, this is how mine fits in all the stuff.
Actually, before doing the sum of Gaussians, we tried first with a particle filter, but you need too many particles.
Oh no, I'm sold on that.
Okay.
It's more the
No, but we really tried.
all the delay state filters that people have done, I think could be done online if you have the right process.
Yeah. I don't see a big problem doing all this online. But.
I had a question on the Hilbert maps. I wasn't clear how you build them. So.
How do you learn them?
Yeah. So you have these virtual points.
Yes.
So I can see once you build the virtual point, you create the Hilbert map. But from the measurements, how do you create the virtual point? Because you seem to randomly sample. So from those samples.
So you have your measurement, you sample your measurement, and then for each of these points, you run one step of the stochastic gradient descent, where you compare what you already learned for that specific point to what you are observing now. And with that, basically you update the weights of the neighborhood of that point.
But the features of the Hilbert map, from how do you go from there to the features?
So these points, first you do the feature map, and then you got a vector in the Hilbert space.
Okay.
Then
and the
that vector relates to some weights of the
virtual point are on a grade fixed by the resolution?
Yes.
Okay.
So that's step.
That's step.
You have this transformation and then these values that you learn.
So in the background you have a grid?
Yes.
Okay.
So when you take the measurement X star there, it influences those 4 neighborhoods.
Well, in this case only these 3, but
okay. Those then do they have influence on their neighbors? Is that how the kind of information propagates?
Yeah. So for each point, what you do is you update the neighbors of that point, all the weights.
Yeah.
And then if the next point is here, I will update the neighbors of that point.
And the Hilbert space seems to be doing a similar kind of trick as SVM. You project to a higher dimension where everything becomes linear.
Yes.
And so how big are those Hilbert space in terms of dimensions in general? Is it,
I don't remember.
From 2D to 10D or 20D? Or?
I don't remember the numbers, but the breakwater is like between 3,000 or 4,000 virtual points. which is a almost 80 meters wide dataset.
One question I had, or it came to mind when Rafa was asking his question, could you make, could you make, like, so he was asking about the resolution versus the neighborhood size. Could you make a quad tree underline, sort of a quad tree-like underlying representation, where you increase the resolution in places where there is something and keep it sort of sparse in areas that are free?
Okay, this is a discussion that we had also. So basically, the problem is that you cannot add points where you already learn something, because you don't know the weight that you should give that point, because every time you learn a point from a measurement, you will throw it and you just keep what you learned. So I cannot add a point here after I already learned this, because this will affect my map directly. The approach that I'm using for 3D, because I know that it's maybe I have too many points, is that I save my features in an org tree.
Yeah.
So, and when I check for the neighbors of a point, I check if they exist in the org tree, and if not, I declare them. So my grid is expanding as I need the space. But it's a coarser grid that if we use a normal org tree representation.
But if you've thrown away the actual observations, can you sort of work, if you wanted to increase the resolution within one of those grids, you can then kind of look at how much weight is in that grid and kind of, you know, subdivide it afterwards, assign it points based on the weightings of the map or something along those lines?
Maybe it's possible, but I haven't seen the theory that supports that.
What the guys could be there, you were saying they change the resolution depending on where you are to have enough resolution. The people doing mobile robotics can't find it. Maybe that's something similar they've done, something like that.
Maybe, I don't know. You should sample a lot of points here and then increase the resolution and check that what you sampled before is the same as the increased resolution now. And then keep learning on this new structure of virtual points.
So if you go to the results with the Hilbert mapping simulation.
Okay.
There. So is that no, the next one I think. Okay.
Terrain based.
Yeah, that keep going. One more. That's it I think.
That's
So the slab results are okay, isn't it?
They are not perfect. Yeah.
Yeah, and so that's why I thought, okay, that works, but how well does it work? And that's why I think the comparison in simulation could have been done quite easily with other techniques. Just to ground, and maybe to also try to get to understand why. So, because you said, well, we can see it's working, but it's not perfect. And my question is, well, tell me why. Why is it not perfect? So do you have an insight of why what are the issues? What are the problems?
The biggest one with this is that we have corners, and we cannot represent corners.
Yes.
That's one of the biggest ones that makes it not work perfect.
But even changing the resolution and there's a number of parameters in your algorithm that you could have
we can
tried and see
it's an easy way to test.
Yeah. So I think there's a bit of work here because if, as a researcher, I look at your technique, I go, that looks really interesting. But before I'm going to invest 6 or 9 months or a year of energy to replicate it, I want to understand how well it's going to work because I might go, for my problem, it might not be adapted.
Yeah.
And without enough details, I think it's quite hard to get So one question I had, so it's a good diagram actually. So using particle filters,
yes.
and normally particle filters take the mean of the particles at the end to get the solution.
Yes.
So that means you would have technically to take the mean, the weighted mean of Hilbert maps. Can you do that? Can you?
Of the maps or the positions?
Well, the maps, because if you have the map at the end.
Yes.
Can you fuse Hilbert maps? So the normal frequency gradient can fuse them quite easily.
But here you're just selecting one trajectory that has the lowest
Yeah,
uncertainty.
that's what I'm
we check the mean, as you've seen in the journal, the mean of the particles, but the trajectory is less stable than taking the best one at the end.
Weighted mean?
Yes.
Yeah, it will be weighted, but that's for the position. My question, okay, make it simple. Can you fuse Hilbert maps? Can you take two Hilbert maps and produce two Hilbert maps and create a new Hilbert map?
Probably.
You know, is there a process? Is there mathematics where you need to fuse two Hilbert maps? Or is it, at the moment, you create an Hilbert map and if you want to...
There is no process that I found in the literature, but
okay.
probably.
So that's why you took the best one, to
Yeah.
do this one.
So you want to take all these versions of the map, no?
That's what I'm saying.
That we had?
And merge them and see what happens. Maybe it's a more stable solution. I don't know.
Maybe. We should.
But you wouldn't get to me how you fuse the maps.
I would expect you wouldn't want to fuse in the maps that where you're going. You kind of end up with.
But at some point, their weight is very small.
We don't know what the weights are there, so it's difficult to tell. Okay, and I think I've covered. Yeah, I think we've covered all the questions. So I want to thank you again for the clarity of the presentation and for the document and for today's contribution. So the next step is we're going to have to discuss it between ourselves. So, yeah, sorry. If anybody with a Ph.D. in the room would like to ask questions, this is your time.
I have some words from
Pere.
So on behalf of Pere, who wanted to be here more than anyone else, he sent me this morning some words. They are in Catalan, don't worry, they are only a few words. So this is what he sent me. Guillem, it's for Guillem, of course. Ha estat un plaer i un privilegi per mi dirigir en Guillem al llarg d'aquests anys. És un dels estudiants més brillants amb qui he col·laborat, aprenent molt en el procés. Estic segur que la seva excel·lència tècnica ha quedat palesa amb la presentació i posterior discussió. Per això vull fixar-me avui a la multitud de coses que ha fet durant aquests anys i que no han estat reflectides a la tesi, els nombrosos experiments dels nombrosos projectes que no haurien estat possibles sense la teva contribució, les ajudes a preparar i impartir pràctiques, la seva ajuda a la resta de membres del grup sempre que ha calgut. Gràcies, Guillem, per tot el que has aportat al grup, però sobretot com ho has fet, amb excel·lència i amb un somriure a la cara. És un plaer treballar amb tu. I will just repeat more or less in English the same, that for us it has been a pleasure to have Guillem all these years in the lab. We thank him a lot, all the work he did, not only on the Ph.D., who was excellent, but also in all the projects he has collaborated, in many campaigns, many last-minute implementations, many I don't know, days, weeks, months that he has been contributing to just having all the projects, vehicles working. That sometimes this is not reflected in publications, but it's very, very important. And that's it. And I would add that I also hope that we can collaborate with him for many more years.